Let's try problem 8.10. A uniform beam of length 1 meter and mass 10 kilograms is attached to a wall by a cable as shown in the figure. The beam is free to pivot at the point where it is attached to the wall. What is the tension in the cable? Okay, so we have a beam over here attached to the wall. It's free to pivot around this point right here. So what this problem is really asking us is to make sure that all the torques are equal to 0. So the first thing to do is just identify the forces that are going to give us a torque. So the first one is going to be the mass from the beam. So this weight of the beam is going to produce a torque. So we'll call it W sub B. And then we also have another torque caused by the tension in this rod over here. But we're only interested in the force that's perpendicular to the rod. And so I'm going to call this T sub F, tensional force. So this cable right here is going to be holding up this rod. So now to write it down in math, the sum of all torques is going to be equal to 0, right? So that way it's not moving. And so this is going to be equal to the torque from the beam, which we wrote down here, plus the torque from our cable. We'll call it T sub C. And so the torque from the beam is going to be equal to Fr sine theta, right? And this is just going to be equal to the force. The force here is just going to be the weight of the beam. So we'll call it m sub b, the mass of the beam, times gravity, and that'll give us our weight. And then the radius is actually is measured from here to the end of the beam. So from this end of the beam to the middle is only going to be 1/2 r, right? Because the center of gravity is going to be in the center of the beam, which is half the radius, which we're given as 1 meter, times the sine of what? So we measure these from a horizontal over here. So from here to here, it's just going to be negative 90 degrees times the sine of negative 90. So just to simplify this a little bit and make it easier for us to write, the sine of negative 90 is going to be a -1, so we'll put negative, and then I'm just going to rewrite the rest, 1/2 r times the mass of the beam times gravity. Okay, so that's the torque provided by the beam, this right here. Now let's go ahead and find the torque provided by the cable. So again, it's just going to be Fr sine theta. And this is equal to, the force here is just going to be the tension force, which I'm going to write as a little t, tensional force, times r, which is just going to be regular r, right, because it's from the wall to there, so that's going to be just r. And then the sine of theta. So theta here, again, we measure from the horizontal. So this angle from the horizontal all the way over to here is going to be 150 degrees. Okay, so the sine of 150 degrees is just going to be 1/2. So we got 1/2 times the tensional force times r. Okay, so now we have T sub C and T sub B. So now let's plug them all in. So the sum of all torques is going to be equal to 0. It's going to be equal to the torque provided from the beam, which is -1/2 times r times the mass of the beam times gravity, plus the torque provided by the cable, which is going to be 1/2 times the tensional force in the cable times r. And so we can rearrange this, right? Add 1/2 r times mb times m sub b times g to both sides, and we get 1/2 r m sub b times g is equal to 1/2 times the tensional force times r. And now our r's cancel out, our 1/2s cancel out, and we're left with just tensional force is going to be equal to the mass of the bar times gravity. And so that's going to be the tension in the cable right here. And that's problem, let's actually put some numbers to this first. So the mass of the bar is 10 kilograms. This is equal to 10 kilograms times 9.8 meters per second squared. And so the tensional force is just going to be 100 newtons. And that's problem 8.10.